Experiments with waves provide a practical way to understand the fundamental properties of wave behavior, such as speed, frequency, and wavelength. One common experiment involves using an oscilloscope to measure the speed of sound. An oscilloscope is a device that visually displays waveforms, allowing you to analyze the characteristics of sound waves in real time. To measure the speed of sound using an oscilloscope, you would typically set up two microphones a known distance apart, connected to the oscilloscope. A sound is then produced near the first microphone, and the oscilloscope captures the time it takes for the sound to travel to the second microphone. By measuring the time delay between the sound wave reaching each microphone, and knowing the distance between the microphones, you can calculate the speed of sound using the formula, speed equals distance time. This experiment provides a direct way to measure how fast sound waves travel through air. Another fascinating experiment involves measuring the speed of water ripples using a lamp. This can be done by creating ripples in a shallow tank of water, often called a ripple tank. The tank is illuminated from above by a strobe lamp or an overhead light source. The light casts shadows of the ripples onto a screen or the bottom of the tank, making the wave patterns visible. To measure the speed of the water ripples, you would first determine the wavelength by measuring the distance between consecutive peaks of the ripples on the screen. The frequency of the ripples can be adjusted and measured using the strobe light. When the frequency of the strobe matches the frequency of the water ripples, the ripples appear stationary. By knowing the frequency and the wavelength, you can then calculate the speed of the water ripples using the wave equation, speed equals frequency times wavelength. This method allows for a clear and visual way to study the movement of waves on the surface of the water. The wave equation is also essential when experimenting with waves on strings, such as a guitar string or a string attached to a mechanical oscillator. In such an experiment, you can observe standing waves, which are patterns that form when waves of the same frequency and amplitude traveling in opposite directions interfere with each other. The wave equation, speed equals frequency times wavelength, is used to analyze the speed of these waves on the string. To conduct this experiment, you would typically fix one end of the string while the other end is connected to a vibration generator that produces waves at a specific frequency. As the generator vibrates the string, standing waves form at certain frequencies known as the string's resonant frequencies. By measuring the length of the string and the number of nodes and antinodes, points of no movement and maximum movement, respectively, along the string, you can calculate the wavelength of the standing wave. With the frequency known from the vibration generator, you can then use the wave equation to calculate the speed of the waves traveling along the string. This experiment helps illustrate the relationship between the physical properties of the string, the frequency of the waves, and their speed. These experiments with waves using an oscilloscope to measure sound speed, a lamp to measure water ripple speed, and the wave equation for waves on strings provide hands-on ways to explore and understand the fundamental principles of wave behavior. Through these methods, the theoretical concepts of wave speed, frequency, and wavelength become tangible and observable, enhancing the comprehension of how waves function in different media.